Okay, so one of the special, topics or subtopics involved in stoichiometry is the idea of a water of crystallization. So here's an image here. You have hydrated copper sulfate with water, it's blue, and anhydrous copper sulfate without water is white. It's a test for water, actually. And essentially, around the crystal of copper sulfate, which of course is an ionic molecule, is going to be these waters of crystallization, which actually it's the waters of crystallization around the copper ion that actually give copper sulfate the blue color. Okay, you can actually calculate how much water there is around a ion using stoichiometry, and that's what today's lesson is going to be about. So, water as crystallization refer to the water molecules that form an essential part of a crystalline structure. The empirical formula of water of crystallization is written with a dot between the compound formula and the water component of the crystal. So for copper sulfate, you have the copper sulfate crystals, and then you have 4 waters as the waters of crystallization and a dot between the two. So you can actually calculate how many waters of crystallization there are per crystal of the ionic salt. And the best way to show this is through the example I'm going to put forward. So you have a sample of hydrated barium chloride, and then what happens is you heat it and it removes all the waters of hydration. And you can calculate how many waters of hydration there are by taking measurements. And in this example, the mass of the crucible and lid is 26.49 grams. The mass of the crucible lid and hydrated barium chloride, so this is the water, is 27.74. You heat it once and it ends up having a mass of 27.6. You heat it a longer time and it ends up having a mass of 27.55 grams. So from these numbers you can actually work out how many waters of crystallization you have per crystal. And the next slide will show you how. So it's key, there's a little trick question they sometimes use in exams, to ignore the first measurement, the first heating, because that's not when all the waters of crystallization have left. That's only when a few have. Okay, so the first thing you have to do is calculate the mass of the anhydrous barium chloride and the water. So that's when all the water's been removed. Okay, so there's 2 things. The anhydrous barium chloride, when all the water's been removed, and the water, which has been removed. So to work out how much your anhydrous barium chloride, the mass of that is you take the mass of the crucible and the lid when you've had the second heating, when all the water's been removed, and subtract it from the mass of the crucible and the lid. So that means that the amount of barium chloride without any water is 1.06 grams. Therefore, the mass of the water is going to be the mass of the hydrous barium chloride, the barium chloride at the start when there was water, minus the mass of the barium chloride once all the water is removed. So it's also got to include the mass of the crucible and the lid along with it. So it's going to be 27.74 grams at the start minus 27.55 grams at the end. So that means the water that's been removed is 0.19 grams. So then the second step is you've got to calculate the molar mass of each. Okay, so the molar mass of barium chloride from our periodic table is going to be 137 plus 2 times 35.5, 208 grams per mole, and the mass of water is going to be 18 grams per mole. Okay, so now we've worked out the molar mass of each, the salt and the water. The final step is to calculate the number of moles for each. So the number of moles of barium chloride is going to be mass over molar mass, so it'll be 0.0510, and the number of moles of water is going to be, again, the mass of the water minus, divided by the molar mass, which is going to be 0.106 moles. So therefore the ratio, again by dividing by the smallest, is going to be a 1 to 2. Okay, so, and finally, use the ratio to work out the formula. So it'll be barium chloride dot 2H2O, and that's the answer.